Hello and welcome to Lecture 4 of the Energy Unit in Phys 1104. We spent last lecture looking at elastic collisions. Now we're going to look at other types of collisions. Our original definition of elastic collisions was that the relative speed of the two objects in the collision is the same before and after the collision. And what we call a totally inelastic collision is when the relative speed after the collision is zero. Just plain old ordinary inelastic collision, not a totally inelastic collision, is anything in between those, where now the final relative speed is just some fraction of the original relative speed. And so I'm putting this number e in front. That isn't the e 2.71 blah blah. No, this is just a coefficient. It's some number that's saying what fraction of the initial relative speed is the final relative speed. We call it the coefficient of restitution. The word restitution means sort of restoration. How much of the original relative speed is restored to the system after the collision is over. And so you can just say that the coefficient of restitution for the collision is defined as the ratio of the final over the initial relative speeds. And for elastic and inelastic collisions, that means then that the coefficient of restitution is between 0 and 1, where it would be 0 for a totally inelastic collision and 1 for an elastic collision. Let's use this for a fairly realistic situation. So here's a bowling ball and a bowling pin, and these inertias of the bowling ball and the bowling pin are according to USBC regulations, and the US Bowling Congress also has regulations around the coefficient of restitution of balls and pins, and they say that the coefficient of restitution between a ball and a pin should lie between 0.65 and 0.75. So let's suppose in this case it's 0.7. And let's find out, in this situation with the ball coming along at 6 meters per second, how fast the pin is going immediately after the impact. And I've put a reminder here to you of how the coefficient of restitution is defined in terms of relative speeds, and we'll need that. So first of all, we should think about whether the system is isolated. And if you remember way back when I first started talking about conservation of momentum and experiments where you're looking at interactions between, say, carts, and you can't completely get rid of the friction, one of the issues is that if the whole experiment is over quickly, then the external interactions don't have much time to affect it. And the collision between a bowling ball and a bowling pin is very, very fast. They're both hard, and so the collision is over in a tiny fraction of a second. And so it's going to be a very good approximation to say that the momentum is conserved. So working with an x-axis to the right and noting that the initial velocity of the pin is 0, I can write down the conservation of momentum like this. Where note that there's no term here on the initial side for the pin because it's not moving at all. Even though this is now an inelastic collision, the solution is actually going to go a lot like the elastic collision that we did in the last lecture, because we don't know either of these final velocity components, and so the conservation of momentum equation is not enough for us to solve. So we're going to need to use our x component of relative velocity again, just like we did last time, except that we have a twist. So first I'm going to write it down the way we had it last time, right? So we would have the relative velocity, say, ball, and this is the x component of the relative velocity, minus pin, all initial, all equals the negative of that same relative velocity component after the collision. This would be what we would use if this collision was elastic, but it isn't. And so the ratio of these components of the relative velocity is going to be e. And so if you think of rearranging this, you get E times VI equals VF. And so I need to multiply all of this by E. And that's the new form of the equation that is going to work for this inelastic collision. And I'll note that this V pin initial is 0, and that's going to simplify things for us nicely. So now we should proceed as before. We should eliminate one of these unknowns by solving from the simpler of the two equations and substituting into the other one, and then we can solve for what we want. So since we want how fast the pin is going, we can just eliminate VBFX. So I'm going to leave this to you. Here's your strategy. Solve for the final x component of the ball's velocity out of the relative velocity equation here, and substitute that into the conservation of momentum and rearrange to solve for the thing we're looking for. So you should pause the video and do that, and when you come back, I'll have done the algebra too, and you can check yours against mine. So there's my algebra in all its glory, right? I solved for VBFX. I substituted it back into the conservation of momentum. Here it is, substituted in. I solved for VPFX. I did a bit of simplification, and I plugged in our original numbers and came up with 8.4 meters per second as a final answer. And I'll just do a unit check. We have kilograms over kilograms, which cancel. 1 plus E is a dimensionless number, so that all is fine, and so we have our meters per second from our V here. One final thing we should look at is explosive separations. So, as always, in an explosive separation, if the system is isolated, momentum will be conserved. But this is an interaction where the relative speed of the two objects is larger after the collision than it was before the collision, which implies that the kinetic energy increases. Well, our hypothesis is then that that means we must have internal energy in the system that's being transformed into kinetic energy. So the system needs some source of internal energy. So my favorite type of explosive separation is a literally explosive one, because you do it with explosives. When you have two rocket stages and you need to separate them because, say, you're discarding a lower stage of your rocket, there are explosive bolts that go off to separate them and push them apart. So the energy here is chemical energy. The internal energy that's being converted into kinetic energy is chemical energy in those explosives. Of course, there are many other ways you can have internal energy in the system that gets converted into kinetic energy. Any sort of internal energy generally can somehow be transformed into kinetic energy to give you an explosive separation. You might be starting to think that the kinetic energy isn't all that useful. I went through all that effort to develop it, and I've barely used it because the relative speed has been a more useful thing for solving these collision questions. Well, that's about to change, and as we go farther into the course, the kinetic energy will be more and more useful. As soon as you get out of simple collisions, the relative speed is of no use whatsoever, but the kinetic energy is. So here's an example. Here's an explosive separation. It's not a very exciting explosive separation. We could do this in the lab without destroying anything. So we've got two carts, and we've compressed a spring between them. And perhaps we know, because we've already, say, used this spring to launch a cart and measure its kinetic energy, that when this spring is compressed by this amount, it has an internal energy, a spring energy, of 3 joules. And we know the inertias of the carts, and we would like to know if we now release it so that the spring expands and pushes both carts away, how fast are those carts going after that process? So there are no significant external interactions because of the low friction, and so this should be an isolated system. Also, there's nothing feeding energy into the system or stealing energy out of the system. This should be closed, and so we should be able to use both conservation of energy and momentum. let's just draw the bar chart for that. So we know that initially we're going to start off with a whole bunch of spring energy. And then after the spring is expanded out to its ordinary length, it's not storing any energy anymore, and all of that gets converted into the kinetic energy of the carts. So I'm assuming the spring plus the carts is our system. And this is the energy energy bar chart then that describes this process of going from internal energy into a kinetic energy. And this kinetic energy is going to consist of, remember, it's extensive, and so it has to just be the kinetic energy of cart A plus the kinetic energy of cart B. So I'll call these all finals. And so there is my conservation of energy equation. I'll just rewrite it up here. I've got E internal initially equals K A final plus K B final. And I could rewrite that all. Maybe I will. I'll say, and I'll call it VAF, but that is the speed, but it's moving along the x-axis, and so that is just the x component squared plus a half, and I'll do the same thing here and write this in terms of this component, B. And then I also have conservation of momentum. Well, initially the momentum's really simple. It's 0. And so then after the process, I've got an MA VA final X. Note, I know it's that way, but I don't need to write any negative here. I believe this X component of the velocity of A is negative. So there we go. And again, I've got a situation where I've got two unknowns. Right? I've got both of these final velocity components that I don't know, but that's fine. I've got two equations to solve with. Oops, I forgot a square. This looks maybe intimidating because of the squares here, but notice you're just going to be able to very easily solve for one velocity component in terms of the other and substitute it into here, and you'll have an equation with only one unknown and a fairly simple equation. So I'm going to suggest that you should solve for VAFX and substitute that into the other equation and then solve for VBFX. And so pause the video, and when you come back, I'll have done the algebra too. So there it is with the algebra all done. I've solved for VAFX. I've substituted that into the conservation of energy. I then did a little bit of rearrangement, and I came down to this expression, and this now works out really easily. It ends up being the square root. We've got 2 times E in, and E in is 3 joules. So that's 6 joules up here all over, and this is 2 kilograms squared over 1 kilogram. So there's 4 kilograms squared over kilograms is kilograms, plus MB is 2 kilograms. And so we've got 6 joules over 6 kilograms under the square root. So remember, a joule, so that's 1, right? 6 over 6. A joule is a kilogram meter squared per second squared, and that's all divided by kilograms. And so that comes out, well, square root of 1 is certainly 1, and square root of meter squared per second squared is meters per second. Good. This is a velocity component. It had better be in meters per second. And so there we go. There is our one velocity component, and you could easily now plug that back up into this equation to get your other velocity component.